Soil formation is a continual process. However, the results are very gradual. In fact, to develop just 1 inch of topsoil may take hundreds to thousands of years. Soils are organized into visibly distinct layers through the interaction of the 4 soil-forming processes: additions, losses, transformations, and translocations. Additions refer to material which is added to the soil, such as organic matter, water, or new mineral materials deposited by wind or water. When soil particles or chemical compounds exit the soil, losses occur, and these alter the chemical and physical composition of the soil. As sand becomes chemically weathered and smaller clay minerals are formed, organic matter transforms into decay-resistant organic compounds known as humus. Translocations refer to the movement of soil components within the profile. Over time, soil-forming processes create visibly noticeable layers called horizons, which possess distinct characteristics such as color, texture, chemical composition, and structure. The continuous weathering and soil horizon development process leads to the development of a soil profile. A soil profile is the vertical display of soil horizons, which gives valuable insight into the origin and characteristics of soils in an area. There are 5 basic soil horizons: O, A, E, B, and C. The O horizon is made of organic matter or partially decomposed organic matter and is usually black or dark brown. The O horizon is typically formed in forests through leaf and woody material deposition. The dominant processes responsible for genesis of this horizon are additions of organic matter and transformations of partial decomposition of organic matter. An A horizon always forms at the surface and is most commonly referred to as topsoil, as it is comprised of minerals, decomposed organic matter, and large amounts of microorganisms. A horizons are commonly found in grasslands, where annual additions of leaf material and roots contribute to a dark, rich-looking soil layer. This horizon may be buried by natural events where it is no longer found at the surface, which indicates the soil and landscape process have changed at some point in the past. The dominant processes of A horizons are additions, transformations, and in some cases, losses due to erosion. The E horizon is much lighter in color than the A horizon. These horizons are more common in forested areas because there is more precipitation and an acidic forest litter layer. E horizons may form in wet depressions in lower precipitation grasslands due to landscape hydrology. The E horizon is known as a layer of eluviation or loss, since water moving through this layer carries nutrients, organic matter, and soil particles into the layers below. E horizons form primarily as a result of translocation processes. Known as the zone of illuviation or deposition, a B horizon is a mineral subsurface layer which receives materials translocated from the E horizon. The accumulating materials include clay, soluble salts, and/or iron. Soil erosion may cause overlying horizons to be stripped, leaving a B horizon at the surface. Translocation is the dominant process forming B horizons. The C horizon consists of unconsolidated parent material with little to no alteration due to soil-forming processes. Minimal additions and losses of highly soluble material may occur, but mainly low-intensity processes, such as movement of soluble salts, are present. Soil formation is affected by 5 factors: parent material, climate, biological factors, topography, and time. These factors each interact with one another and play different roles in the soil-forming process, depending on the region in which the soil is located. Most soil formation processes begin with parent material, which is comprised of various mineral materials and is the base from which soil is formed. The composition of parent material has a direct impact on soil chemistry and fertility. Parent materials rich in minerals containing soluble ions such as calcium, magnesium, potassium, and sodium easily dissolve in water and are readily available to plants. These minerals give rise to fertile soils. Parent materials low in soluble ions may be infertile and unsuitable for agriculture or require additions of more fertilizer. The mineral material plays a huge role in the type of soil developed and the rate at which soil development takes place. Mineral material includes weathered rock, volcanic ash, and sediments which were moved and deposited by water, wind, or ice. Vegetation and animal matter deposited on or in the soil contribute the organic material. Soil parent materials are categorized based on the mode of transport.
Some of the very common ones, say here in the United States, would be what we call alluvium, which is really any material that is deposited by running water. We have a lot of glacial deposits, especially in the northern part of the United States, and these are deposits that were created by the last glaciation. We have a lot of wind-blown parent materials. Here in the Pacific Northwest, that includes volcanic ash that's come from the eruption of some of the volcanoes in Washington and Oregon. We also have a lot of wind-blown silt-sized material called loess, which here in the Palouse is a very major parent material. And the parent materials are really going to vary according to where you are. Each part of the country tends to have their own unique assortment of those parent materials.
Weathered bedrock is composed of material which is too hard for root growth. Soil formation in bedrock is slow because the rock must first fracture before other soil-forming processes and plant growth begins. Glacial till is unsorted sediment which is deposited directly by glacial ice. This form of parent material is often highly variable in particle size and contains everything from boulders to small gravels. If highly weathered, glacial till can make for excellent farmland. Colluvium is parent material which develops from rock fragments which fall from greater heights due to gravity. Due to this, these soils are usually coarse and stony mixtures of particle sizes and dominate along the base of mountain slopes. Lacustrine parent material is transported by lake water. This parent material is composed of fine particles and is devoid of coarse particles such as coarse sand or gravel. Lacustrine deposits are well sorted and possess thin layers which reflect annual deposition of these sediments. Marine deposits are sediments found in an oceanic or coastal environment. These sediments are predominantly of sand to clay size and are devoid of coarser particles. Marine deposits are very well sorted, yet usually contain no layers. Aeolian sediments are silt and occasionally sand-sized particles which have been deposited by wind. These materials are well sorted and devoid of coarse particles. Alluvium is sediment which has been deposited by flowing water and is the parent material of soil on floodplains. These materials are usually stratified and found along streams and rivers. Parent material is a mixture of rocks and the minerals within those rocks. Soils form from parent materials through processes called weathering.
Weathering is really you might think of the human analogy as the process of aging. You start off with a baby, or you start off with a very young soil, and over the course of their lifetime, the soil ages, and in doing so, it's really driven by weathering. So if we look on one end of the spectrum, we've got a young, undeveloped soil that is really doesn't have a lot of distinct characteristics at that point, and through the process of weathering, it may turn into a very old soil that is maybe not unlike a senile person, kind of over the hill. In other words, a lot of the minerals have weathered out of it. It's essentially turned into something like a rust pile, for example. And that would be a real extreme example, but it's all driven by the process of weathering.
Weathering occurs in two ways, chemical and mechanical. Chemical weathering alters the internal structure and composition of minerals by the addition, removal, and transformation of elements. In contrast, mechanical weathering is the breaking down of rocks into smaller particles in which each new fragment contains the same exact properties as the original rock. Weathering is dramatically influenced by climate, mainly water and temperature, which drive the majority of physical and chemical processes. Climate plays a large role in soil formation.
Temperature is something that is extremely critical for soil formation just because it drives biological processes. The warmer temperatures tend to increase biological processes. Warmer temperatures increase the rate at which chemical reactions occur. And I think those are certainly a big part of the soil formation scheme. Temperature is going to be very influential in that it really dictates a lot of the biological activity. In other words, what types of plant communities you might find on a soil is going to be dependent on the temperature. And it also is very influential in terms of determining the activity of microorganisms in the soil. The warmer the temperature, generally the greater the amount of microbial activity. The temperature also drives the weathering reactions, with warm, humid climates tending to be where you would expect to find the most weathered soils, whereas in a cold climate you're generally going to see soils that have not undergone a whole lot of weathering in most cases.
The biological factor, sometimes referred to as the organism factor, refers to the plants, animals, microorganisms, and humans which have influenced soil formation. Biological factors are greatly influenced by climate and changes over time. Plants or vegetation are usually the most important of these factors. Plants contain roots which open channels in the soil and contribute organic matter in and on the surface of soil profiles. Animals mix the soil by forming burrows and pores through the soil. Soil microorganisms are responsible for decomposing organic matter in the soil and recycling the nutrients in it to inhibit plant production. Soil is heavily influenced by humans through agriculture, urbanization, grazing, and forestry.
Topography is the position on a landscape that a soil occupies. And generally we think about topography or describing topography in terms of a slope gradient. In other words, how steep is a slope? Generally, soils that form on really steep slopes may tend to erode about as quickly as they form, so you don't expect a net soil development to be very great. Whereas on level surfaces, water that strikes that surface tends to move downward through the soil, and that kind of drives a lot of the soil forming processes.
Aspect also influences microclimates and how warm or cool a soil will be. The term aspect refers to the particular direction a slope faces, such as a north-facing or south-facing slope. Soil undergoes many changes over time as it is continually evolving and developing. Time allows the climate and biological factors of soil formation to influence parent material on the landscape. In general, the older a soil is, the more developed the profile will be, with more horizons and differentiated features such as color, texture, and chemical composition between the horizons. Interactions between and among the 5 soil-forming factors are many and complex. These interactions give rise to the vast diversity of soils we see today. For example, consider the range of possible climates and how much climate affects vegetation, which in turn affects the amount and type of organic matter produced, and the other organisms, large and small, which inhabit an area. Or consider how different temperature, moisture, and vegetation can be on a north-facing side of a hill compared to the south-facing side.